Hi guys, today I'm going to take the opportunity and do a couple of more example problems with you guys over this chapter. We did one today where we were dealing with three charges in a line. This PowerPoint, or rather this collection of practice problems, is going to be dealing with charges that, well, for the first part, they are not in a line. We're going to start dealing with charges that sit at right angles to one another. So let's take a look at the first example. Ooh, that's not it. That's it. All right, in this example we have three charges. We have our +1 charge up here, and then we have a +2, and we have a -3 charge. And these guys are sitting at right angles to one another, or in a right triangle. I've made this right triangle be a 3, 4, 5 triangle just to make it easy, but it might not be that way in your math problems for your homework. So for this particular example, the way that I've drawn it is I would like to know what is the net force on the -3 Coulomb charge. What is the net force on this guy here? Now he's experiencing forces that act at angles to one another, so it's not going to be as simple as just adding them or subtracting them together. So the very first thing we need to do, since we've got three charges in a triangle, is we're going to figure out what the angle of our triangle is. So to do that, I'm just going to do inverse tangent of 3/4, or opposite over the adjacent side of the angle. That's going to get me 37 degrees. Make sure your calculator is in degrees for all of this. Radians will give you the wrong numbers. So once I've figured out that this here is 37 degrees, now I'm going to draw my force vectors. I'm going to draw my two forces that this particular charge is experiencing. One is going to be an attractive force towards the +2, and the other one is going to be, I drew it as a repulsive force. So we will go back and change this to be negative. There, that makes a little bit more sense with the rest of my drawing. So this is -1. So now it's experiencing a repulsive force away from that -1 charge down in this direction. So these are the two force vectors I have to solve for. So this is my -3 charge just redrawn, just to show the vectors themselves without the triangle. So this is the first vector this way, going horizontally. And this is the charge between, or the force between this -3 and this +2 Coulomb charge over here. Now I'm going to really highly suggest that when you guys do these problems, just make everything be positive. When you add or subtract your force vectors, by looking at the picture, you're going to know whether or not you're going to have to add or subtract them, or whether or not it's attractive or repulsive. So this negative-positive thing almost becomes a little bit superfluous. So the first thing I'm going to do is figure out this force here. It's a force between 2 and 3. So here's my 9 times 10 to the 9th, plus second charge, I'm sorry, times the +2 times -3 divided by 16. So that force is this, and then my other force, which is this diagonal vector here, is going to be 1 times -3 divided by 25. Remember, 25 is going to be the 5 squared. The distance between those two charges is 5. So this is the force I get between those two. So if I redraw my picture with my forces labeled, I've got my 3.4 times 10 to the 9th going horizontally, and then I've got my 1.1 times 10 to the 9th going diagonally. Now we learned before when we talked about forces, we can't add these together unless they're traveling in the same direction, or if they sit at right angles to each other. So if I can take this angled force and split it into its x and y components, I can add that to my already existing horizontal force here. So we've discovered in the first slide that the angle of our triangle is 37 degrees. So if this angle here is 37 degrees, that means that this angle here is also 37 degrees. And we can use our previous expressions for finding the x and y parts of our force to figure these two legs of our triangle out. So this makes my horizontal force be 1.1 times 10 to the 9th times the cosine of 37. And this is 1.1 times 10 to the 9th times the sine of 37. So I'm going to redraw these three. Now I've got three vectors. I've taken this one vector here, and I've split it into two parts, and I have my already one horizontal existing part. So I'm going to redraw it so it makes a little bit more sense. My previous horizontal existing force, remember this is the force between 2 and 3 here, And these two vectors represent the force between 1 and 3. So, once I draw these, I can see that all my vectors sit at nice right angles to one another. I can subtract the ones that are traveling in opposite directions. So let's do that a little bit first. So when I do that, I get a net force of 2.54 times 10 to the 9th going towards the left. I still have my down vector, but now my over and down vectors sit at right angles to each other, so I can use Pythagorean theorem to figure out my resultant. Now remember, you have to add vectors tip to tail, right? So I'm going to move this guy over here. So my resultant force should travel in a diagonal somewhat like this. So after I do Pythagorean theorem, and I square this, and I add it to the square of this, and then take the square root of it, you should get 2.62 times 10 to the 9th as your net force, traveling in this general direction. I might ask you guys to find the angle at which it's traveling, but for right now, let's just focus on finding the magnitude of the net force, which is what we did here. Which, when you think about it, kind of makes sense. If this charge is negative, this charge is negative, and this charge is positive. It will be attracted over here, but repelled away from this guy, so it's going to kind of travel at a funky looking angle. Alright, the next kind of example problem I want to talk about is what do you do when you are trying to make charges cancel each other out? So let's say, for example, you have two charges sitting in a line. Where does the third one need to be in order to experience equilibrium? Remember, equilibrium means you are experiencing no net force, or no net force, or all the forces acting on you are 0. So let's take a look at a quick example. This picture looks a little bit confusing. There is a similar example in your book on page 640. If you guys don't understand this example, you might want to read through that one. It's very similar to the one that I've done here, just with slightly different numbers. So let's say I have two negative charges, -3 and -5, and they are 2 meters apart from each other. Where would I need to put a positive charge in the center here so that it experienced no net force? We want it to be at equilibrium. So this is no net force here. So we are assuming it's going to be placed some distance r from one of these charges. So I just labeled this distance from the first charge to the second as r. If the whole thing is 2, then that means that this distance between here and here is 2 minus r. So, in order for this guy to be at equilibrium, the force it experiences from 1 has to be equal to the force that it experiences from 3. And that's what this expression says right here. When these two forces are equal, this guy is at equilibrium. So, I'm going to drop Coulomb's law in for each one of these expressions. So, the force between 1 and 2 is going to look like this. And the force between 2 and 3 will look like this. So I've got k's on both sides of my equation, so those can cancel out. I've also got 2 times 10 to the -6 on both sides, so those can cancel out. Now I'm left with this expression here. Now I've got 10 to the -6 appearing on both sides here still, so those can go away too. So now I'm just left with this much simplified expression. -3 over r squared equals -5 over 2 minus r squared. I can do a little cross multiply. I get this. Now from here, there's probably a few ways you can do it with regards to expanding this squared, but I think if you did that, you'd have to do the quadratic formula, and that's just gross. Nobody really wants to do that if you don't have to do that. So instead, I'm just going to take the square root of both sides. So if I square root r squared, I get r, square root of 5, equals square root of 3 times 2 minus r. Now, after that, I can just simplify everything. I'm going to divide both sides by square root of 5 times 2 minus r. That gets me 0.77 times 2 minus r. Then I'm just going to distribute this 0.77 through my parentheses, and this is what I end up with. I'm going to collect like terms here. 0.77 plus 1r is 1.77r. And then I'm going to divide. And I get r to be 1.14 meters. Now, that means that this second charge has to be placed 1.14 meters away from this first one. So if the whole length is 2 meters, then that means the distance between charge 2 and 3 is 0.86. So guys, feel free to review this video. If it helps, like I said, look at page 640 in your textbook for the example problem on equilibrium. There's also an example problem in your book on page 638 for the right-angled problem that we did earlier. But if that's too confusing, you might want to give it a shot just to watch the video one more time. I'm not going to give you guys any on your own practice. We will just do that tomorrow. Just bring your notes and bring your textbook to class tomorrow. I'll see you then.